Hey everybody, and welcome back to Linear Algebra Online. So I want to start off today and actually kind of go back to a problem we talked about in the last video. So if you remember, the dimension of the row space of A and the dimension of the column space of A, where A was that matrix right there, both of these were 3. And you can go back and watch the video when I talked about what those 3 basis vectors could look like, or those 3 vectors that make up the basis could be. And it's reasonable, because they were both the same, to think that for like any arbitrary m by n matrix, the dimension of the row space of C would probably equal the dimension of the column space of C. And that is actually true. And even furthermore, there is a connection between the rank of a matrix and the dimension of the row or column space. And if you go back and look at this example and how we did it, the rank of the reduced matrix, like in the RREF form, is the same, here. It's like what you kind of need to do to figure out the rank, right? You can't just look at this and say the rank is 4 or something. So it turns out that this is actually basically our definition of what rank is. I actually have it on the next slide, but it's right here. So rank of a matrix is the dimension of its row and column spaces, and is denoted by rank of A. So it is literally, that number of vectors in the basis for the row and column spaces. All right. And we can actually prove a very short but important result. So this is kind of another justification for this kind of idea behind the transpose. Like, the rank of A transpose is equal to the rank of A. It's basically like giving us even more justification for why we can like switch back and forth and not like really be doing a different problem in linear algebra. This A transpose matrix has the same exact rank, which is a very important result, as the original matrix A. And the proof is quite short, but it shows like some good techniques with how we like use rank. So the rank of A transpose, by definition, is the dimension of, say, the column space of A transpose, right? But the, we've done these problems where the column space of A transpose can flip-flop, like this part, can flip to the row space of a regular matrix A, right? And then the dimension of the row of A is, by definition, the rank of A, right? And that does it. That's literally like the proof. So this is actually a very like common technique in linear algebra, is to like write rank as a dimension of one of those column or row spaces. And it really doesn't matter which one you pick, because, back here, they really are truly identical. Those 2 dimensions should always be the same. So you can say the rank equals this or this. But that's really like notation-wise how we write rank. It is one of these or this or both. All right. And just a little more kind of formalism here. So there's this notion of the nullity of a matrix, and the nullity is the dimension of its null space, and it is denoted by nullity of A. So it's the number of linearly independent vectors in the basis for the null space. And the nullity is really just another name for, what I've been calling it before is like the number of free variables. And like when I teach linear algebra, I always like when I introduce this idea to you early on, I like really just want to use this, but we just have so much to do to build up to these terms. But no one really uses this. I mean, they kind of maybe use it in passing, but they would really just say the word nullity if they want to talk about the number of free variables. So like if they say, oh, the nullity is 5, they're talking about it's got like a 5-dimensional basis for the null space. And we can take this theorem that we, theorem, I guess, in quotes, that we did before, and it turns into this, because this number of free variables right here is really denoted nullity of A, right? And then n is n, and then the rank of A is the rank of A. So let's have all that. And then all we're doing, right, is we're taking this and we're moving it over. And for some reason, this is actually how you see like this is like the formal rank theorem that you'll see in like a linear algebra book. For some reason, they change the order of it on you when they do this. But if you think about what it's saying the number of things that go to 0, right, in the linear transformation, the things that disappear, the size of those things, right, plus the size of the things that actually transfer, right, should equal the size of the matrix, which is not a very brilliant statement. If you have a 3D, I'm actually going to make this a little smaller because I want to draw a picture. Formal rank theorem. So, if you take 3D space, okay, and let's just say, you were actually mapping on all of, 3D space here. So you had all this different stuff, right? Some transformation happens, takes 3D space, and it maps it down to just, say the plane that cuts through just the XZ axis right there, okay? So that would mean that there's a dimension 1 that you're losing, right? Because you're taking 3D down to 2D. And so we lose 1, so nullity is 1, and then the rank of A is 2, because 2 things transfer. And 2 plus 1 is 3. So it's actually simple, but very, very, very important to make sure that you understand what a transformation is doing. I can actually now show you guys some of like the work I did in my grad stuff, and I'm going to actually show you in class an example of how I use these to do all these different really complicated maps between vector spaces, basically. So very important, but also not that hard to use. Basically says how many things get lost. In this case, 1 dimension gets lost, and 2 dimensions get transferred. 2 plus 1, 3. All right. I want to prove this rank theorem for an M. I think I wanted that to not be n by m. I think I want this to be m by n. Don't know if it matters too much, but I'm going to do m by m because that's kind of the standard way. So I'm going to go ahead and just basically prove the rank theorem here. All right, so I'm going to start off, and I'm going to just say, let's let the rank of A equal some like R for R just not greater than M, right? So, the rank can obviously only be up to M, so you can be less than or equal to M. And then that would imply, that the reduced form of that matrix has R leading ones, right? And it would also imply that the reduced form of A has n minus R free variables, right? And so the rank of A was R, and the nullity, which is the free variables, is n minus R. So if you literally just do that out, right, the R's would cancel and you get n. So the rank of A plus the nullity of A would equal n. And that's just like, it's not super formal proof, but it honestly is like the idea here. So always good in linear algebra to make sure you know the intuition though, and I think this is the better intuition to make sure you understand. So what this is saying is if you do something where you take 3D space, you map it down to a plane, you lose a dimension, and you started with 3, and so 2 get transferred, and truly 2 plus 1 is 3. It's basically like conservation of mass is honestly what this thing does. So that's the rank theorem. And I just want to do sort of like 2 more problems. And the first one is kind of more of like a computational problem, and then the last one's like kind of a tricky proof, I guess. So I want to find the nullity of these 2 matrices M and N below, okay? So both of these are basically gonna somehow utilize the rank theorem. And for this one, okay, I'm gonna think, I've only got 2 vectors here, so I'm gonna think about the column space, and like if I call this V1 and this V2, right? Like V1 is not a scalar of V2 or something like that, right? So basically V1 and V2 are linearly independent, right? So the rank, which is the can be understood as the dimension of the column space of, I guess it's M, would have to be 2. It's full rank. So the nullity of M would have to be 0. So that's the kind of thing that we kind of do with like the rank theorem. We basically just use this thing to help justify what the nullity would be. Maybe I should be a little more clear, because this thing is a 4x2 matrix, and so this has the structure M by N, and so the fact that we were getting 2 for the rank, it was like 2 plus 0 equals 2 is the idea. So that's like the first one. For this one, if you do like the reduced row echelon form of it, okay, you're gonna get 1 and then some stuff, and then you'll get 0 and then a 1 and some stuff, and then you'll get a row of zeros. And that is really enough to answer the question, because the rank of this thing then is 2, right? So this thing is a 3x4 matrix. So we know that like 2 plus something equals 4, because that 4 right there, M by N, always that last number. And brilliant math equation here. This has to be 2, and this has to be the nullity. So the nullity of N would have to be 2 on that one. All right. So that's kind of the day-to-day stuff, I feel like, that you do with the rank theorem and all that. Now time for some real math. So there's something that I kind of mentioned briefly called an orthonormal basis, and ortho is perpendicular part, orthogonal, short for orthogonal. Normal is unit 1, length 1, right? And a lot of problems in math, there's actually a whole technique called the Gram-Schmidt process but we oftentimes just need to find an orthonormal basis for something. And we like actually using an orthonormal basis to describe a space. It's like literally why we teach you guys I hat, J hat, and K hat. It's like makes sense and it makes the world work nice. It would be odd to use like a random set of 3 vectors to describe space. These ones work really, really nice. And these are orthonormal, right? An example is just I hat, J hat, and K hat. Those are 3 ortho, this set, I guess I should be really careful about this stuff, forms a basis, the B, and that basis is orthonormal, okay? And it turns out that the columns of an n by n matrix, like, say, Q, form an orthonormal set if and only if Q transpose times Q equals the n by n identity matrix, okay? And this QTQ thing basically shows up over and over again in linear algebra. And we will see it again, okay? And this problem doesn't necessarily have to do with QTQ. It is sort of related, but I'm not going to make a connection at this moment. But for some n by n matrix, the rank of ATA, QTQ, ATA, not AT, Star Wars, equals the rank of A, all right? And this proof is kind of involved, and it uses like some good tricks that I really want to make sure I go through and formally prove it out. All right, and to do this, I'm going to start off, and if you notice, based on the sizes here, right, maybe I'll do this up here, A transpose would be an n by m matrix, A transpose, right? And A would be, it's given as an m by n. And so if you do the product, you would get an n by n matrix, right? And so based on the rank theorem, this is why this is like kind of just super important to get us going, we would know that the rank of A transpose A plus the nullity of A transpose A has to be n, because, this ends with size n right there, specifically that n, right? But also, the rank of n has to equal the rank of A plus the nullity of A, because A is n by n, so it also has to satisfy the rank theorem. So this is kind of the trick. A lot of problems in linear algebra, it's easier to show what disappears rather than what gets transferred. So let me say it again. Always try to show what disappears, what goes to 0, i.e. nullity stuff, null space, things like that, versus trying to show what gets transferred, i.e. rank, things like that. This is much easier to work with, and you'll see in this proof, I think, why it's a little easier to work with. But so since this and this both have to equal n, right? If I can show that the nullity of ATA equals the nullity of A, then I have inherently also proved that the rank of A is equal to the rank of ATA. So that's what we're going to do. So inside of this problem, we're actually going to prove the easier problem, that the nullity of ATA is equal to the nullity of A. And these are sets, right? And so we know that when we prove sets are equal, we have to prove both containments. So I'm going to start off, and I'm going to let x, some arbitrary vector, be in the null space of A, So by definition, AX equals 0. And then from there, we could multiply both sides by A transpose. Right, I'm just sticking like an A transpose on the left here and here. And this part still goes to 0. And so from that line, note that X in the null space of A implies X is also in the null space of ATA, right? Because right there, I'm saying ATAX equals 0, which means X is in the null space. It's in the things that go to 0. So basically, we've proved null space of A is contained in null space of ATA. All right, halfway there. For the other one, okay, I'm going to let X be in the null space of ATA. And so by definition, right, we have ATA equals 0. And this is equivalent to something that seems probably like magical, but it is equivalent to X transpose, like the vectors transpose, right, times A transpose times A equals 0. So basically we just multiply on the left here, both sides by X transpose. You would get that. And this is one of those steps in a math proof that's like really hard to just come up with on the fly. But once you kind of go further in the proof, sometimes you might like realize like, oh, I should do that there. So when you write it up, it looks like you're really smart. But people probably did not just like pull this out of thin air the first time they proved it. So now I'm going to do another weird thing. Okay, I'm going to take the A times X is a vector, right? It just moves this vector X somewhere else. And so I can dot product two vectors, right? It's not a brilliant statement. And I'm going to dot product AX with AX, okay? And dot product has a natural duality, we've talked about this, with the transpose. This is so cool. So we do AX transpose times AX. Those two things really are mathematically the same. And when I introduced transpose, that's how I talked about it. The dot product is identical, has its dual is the transpose of a linear transformation on a vector. So that's true, okay? Now I'm going to use transpose properties, right, which we've built up. And the transpose properties is like socks and shoes things. We got to like reverse that order, right? And look at, I messed up, people. I wanted an X in there because X is in the null space, and I wanted an X right there. Now it's good. So ATAX equals 0 is what it means to be in the null space, right? And then I multiplied both sides on the left by X transpose, so I got that. Now this is the same thing I had up here. So we know that this is equal to 0, right? And this is basically the punchline now. So if like U dotted with U equals 0, then we know that U has to be equal to the 0 vector. And, here, and that just goes back to like Calc 3 kind of dot product stuff, right? Here, U is equal to like AX. So I have that AX equals 0, which is that X is in the null space of A. So I have the null space of ATA contained in the null space of A. And I don't really have the room right here to write it all out formally, but the null space of ATA contained in the null space of A, and then up here, null space of A contained in null space of ATA, implies those two sets are equal, right? Like the only way sets A and B are equal is if A is contained in B and B is contained in A. And that is it.